Welcome to my TED Talk, I guess. Unfortunately for you, I think there are two types of TED Talks. There is a breakthrough leading to a dramatic life change or experience for the speaker. And then the second type has a red logo and fewer protein structures involved. So TED, in this case, is going to be more of the first type. And TED, in this case, stands for the Encyclopedia of Domains, which is this new protein structure classification resource within CATH that we developed with the Orengo and Jones group at UCL. So all the structures that you see here are actually part of that structure, so they're all real. They're not hallucinated. So we started this because as CATH is a protein structure classification resource for the past 25 years, we classify protein domains into homologous superfamilies. And we grew steadily alongside Protein Data Bank. Well, 2 years ago, on my birthday, AlphaFold and DeepMind, they released basically 15 years worth of structures all in one go for us to look into. The first release covered 365,000 protein chains for 21 model organisms. Then we had subsequent releases for Swiss prot, organisms causing neglected tropical diseases. And the last release covers UniProt. But since the first release, we analyzed the first release of AlphaFold database containing the 365,000, and we kind of consider that as a pilot work for what was coming next. So I'm going to glance over this very quickly, but there are 2 or 3 takeaway points I would like you to carry forward to the rest of the analysis. So AlphaFold has been trained on PDB. So AlphaFold is very good at predicting things that are already in PDB. The further you move along from structures that are known, the PLDDT, which is the metric for quality, goes down, and the percentage of disorder also goes up as well. Then the other thing I wanted to take into account is that most of the assignments we were able to bring into CATH at the time, 73%, they come from hidden Markov model matches. But then you could pick up some external relationships using machine learning predictors. And there is still a portion of domains that sometimes we cannot assign to known homologous superfamilies. One of the issues we realized is that when we started looking at the quality of these domains, roughly 50% of domains were good. They looked like something globular. They could belong into CATH. The other half, we didn't analyze them because they had these particular issues. That changes in TED, and that's one of the things we actually worked on to fix this issue. So if you look at this plot now, this is the this is a log scale on the left. You can see here, this is the growth of PDB, CATH, and AlphaFold database, and you can see that the growth has been dramatically. Now we have over 200 million models for protein chains from UniProt. So we had to kind of rewrite our protocols to classify all this data deluge. So the pipeline I developed at the time called CATH-Assign used a cascading approach. And one thing we did to improve it, we rewrote the whole thing from scratch in Nextflow, and now it's more customizable. And we added a couple of new modules in it, specifically to identify better domains in protein chains. This work and this tool, a standalone method developed by Jude Wells in our group, is called Chainsaw. It's a deep learning-based predictor based on a 2D CNN and uses a ResNet style architecture based on TR Rosetta. And then it takes multiple features from inter-residue distance matrices, secondary structure co-membership, secondary structure boundary residues, combines all of it together. And then it predicts soft adjacency matrix, and combined with a greedy algorithm, it tries to predict, is this particular residue part of the same domain as the next one or not? But while we were working on this and aiming to apply it to the whole of AlphaFold, we realized that literally across the corridor, the group of David Jones was working exactly on the same thing. They were going to do it. So we realized this is kind of silly. We should probably work together. And so they came up with this brilliant method called Marizo. It actually borrows some ideas and some modules from AlphaFold, such the IPA module, the variant point attention, and it's trained in a different way. It uses affinity learning. It's trained with a balanced square affinity, and this is a state-of-the-art method. It works very well. So we decided to assemble a TED team that combines our best and brightest, basically. And with a healthy dose of naivete, we decided to go ahead and tackle the whole of AFDB. So to kind of misquote JFK, we decided to do AlphaFold database, not because it's hard, but because we thought it was going to be easy in this case. So we actually encountered a lot of issues in this past 2 years working on this. So AFDB, TED basically, in a short summary, it's the segmentation of AlphaFold database into constituent domains. So as a first step, where's my pointer here? Yes, so there are 240 million protein chains in AFDB, and we filter out redundant sequences. So we start looking at TED 100, what we call TED 100, where we have 100% sequence identical models. And then the other set is called TED redundant, where you have some sequence divergency. Sorry. Then using a consensus-based approach, we use our method, Chainsaw, we use Merizo, and a different method, which is also great, called Unidoc, based on secondary structure elements, but is very fast. We come up with a consensus domain assignment. So the way we've done it, we have a particular domain assignment. We can have 3 levels of confidence. We can have a high consensus, where we have all 3 methods agreeing on the boundaries. We have a medium consensus assignments where we have 2 out of 3, and a low consensus where neither can agree. For the rest of the analysis, we brought over only high and medium consensus domains. This amounts to roughly 324 million domains, which compared to the size of Cath, this is already a 600-fold increase in structural data. Then, using structure, we realized that to determine structure works better than using sequence. You can see here that TED roughly, if you combine TED 100 and TED redundant, we come up with roughly 370 million protein domains. And this vastly outnumbers domains classified by sequence-only resources, such as PFAM, or even our own Cath Gene3D, which is based on either Markov models. And then when we started looking at the composition of these domains, even before we started classifying them, we realized that we almost have an equal split between multi-domain proteins and single-domain proteins. But this is what I wanted to remind you from before. If you look at the quality of domains in TED, we almost have 90% of the domains that are like between 70 and 100 PLDDT. The issue was 50% of the data in AlphaFold wasn't wrong. It's like we weren't looking at the right region in the first place. So using these new methods and a consensus-based assignment works much better. So once we identified these 324 million domains, then we started using, we created a classification protocol to classify them into Cath. This is done on a 2-track approach. We use MM6 with sequence clustering at 50% identity, and then we use a combination of fold-seq, which has been nominated quite a bit, and an in-house predictor for superfamily assignment based on structural embeddings called fold class, developed by the Jones Group. And we have assignments at the homologous level, at the H level in Cath, at the fold level, so CAT, or we don't have an assignment in this case. Using this information for every domain, then we are able to label these clusters. Here you have a distribution of these domains. We have a high proportion of singletons, of which roughly 40% are annotated with a Cath label. And then for the non-singleton ones, we have roughly 26 million clusters with where all the Cath labels are consistent. Then you have some partially labeled ones where we have some divergence between the labels within them, and then completely unlabeled clusters. To go back to what I mentioned before of AlphaFold is trained on PDB, we notice that superfamilies that are expanded already, that are really large in Cath, they have a massive expansion in TED as well. You can see here superfamilies such as the aldolases or the p-loops, they expand massively now. We also have 8 million domains in the p-loops by themselves already. But interestingly, we also see an expansion in superfamilies that maybe have 1 or 2 representatives from PDB, and now we have tens and tens of thousands of domains. Particularly, if you look at the one at the top here, I should probably start using my pointer. Yes, there we go. If you see this particular superfamily here, this MFS, general substrate transporter-like, this is a an efflux pump for antibiotics. So this particular superfamily it was being apparently particularly hard to crystallize, and now we have a lot of different candidates to work on. And this could be really useful to look at drug reuse in this case. So with the help of Vishali in our group, we started looking at, can we use structure to find novel targets for drug repurposing? In this case, this is a chloramphenicol acetyltransferase, which is a common antibiotic. And the proteins on the left, you can see here, these are proteins from a tapeworm affecting dogs. And this is exactly, potentially we can reuse the same antibiotic to treat this disease. But the sequence identity between the actual representative we have in PDB to the one we have in TED is less than 10%. And for the one on the right, this is a trimer from Clostridium botulinum. So this potentially you could use chloramphenicol as well for this, unless you get botulism first. I mean, the next work we've done with this data has been done by Sean in David's group, where he started looking at the presence and the enrichment of interacting superfamily pairs, which are inside that particular chain. You can have multiple domains, and if they are in contact, with which superfamilies do they belong to, and in which orientation in this particular case. So by looking at this domain interactions within chains, he discovered roughly 10,000 interactions that they weren't previously known in AlphaFold in PDB. For example, this particular superfamily here, you have an NTRC-like 2-domain protein, which is highlighted in white. It's always the reference protein here. In PDB, it's only found interacting with a P-loop domain on this particular orientation. But then looking at the TED domains, we also find that it interacts with at least 4 more superfamilies in different orientations and in different portions of the domain as well. So once we finished looking at this data, we started looking at all the things that didn't map to cath specifically. So we started looking at the identification of novel folds. In order to do this, we took we took all the 41 million domains that didn't match a cath label. This comprises singletons with no labels and clusters with cluster representatives from unlabeled clusters. We stripped out everything that didn't pass our quality criteria, and we ended up with 8 million representatives that have good quality metrics. And then we used an iterative clustering approach with FoldSeq, even more stringent at every time, ended up with 625,000 cluster representatives. At the time, then we took the latest version of PDB, and we realized that roughly 200,000 of them, they already mapped to something that was crystallized. And then we searched the remaining ones against a metadom that we call metadom database, which includes the latest version of cath, SCOP, ECOD, SCOP-E, and SCOP2. So by doing that, then we also divided them into novel folds, and then we run them through a symmetry predictor called SIMD to see if we also had some highly symmetrical kind of repeats made structures like Alex just showed. So one thing we realized is that this domain, these novel folds, they're everywhere in the tree of life, but there are also domains on the right. You can see, well, I should use my poster. There we go. You have this distribution of organisms on the right that they are actually enriched in these novel folds. So they have a higher prevalence compared to other species. So here are some of the novel folds that we found. These are not unique evolutionary novelties. They're not found just in one example. You can also have clusters where you have 8,000 proteins where they have this particular domain arrangements. And David came up with a new predictor based on an old idea by Willie Taylor, basically to predict, is this protein similar to a known protein? And then using the reverse of that, he used that as a novelty score. Basically, does this look as far away as something that we saw before? And this is the novelty score that you see over there. So these are the highly symmetrical domains. We're already working on mugs and T-shirts on this, because you can go all the way from these very peculiar extruded repeats that they look like kind of clothing pins But then you can go from 3-fold symmetries all the way to an 11-fold symmetry here for this beta propeller over there. So all the code that we worked on called Cath Alpha Flow, it's written in Nextflow. You can use it yourself. It's publicly available. You can build custom workflows as well. It takes structures directly from AFDB, so you don't have to have a local copy. And in the worst possible case scenario for our HPC, which is 1 gigs of RAM, 1 hour, you can process roughly 100,000 structures. All the modules, though, are also independent. So if you want to run them just to calculate the globularity of a protein or the quality, you can just run those. And in the meantime, Ian has been working behind the scenes to create a new website hosting all this data called, of course, TED Web. And in TED, you will be able to put, at the moment, you can put in a UniProt ID. This is going to retrieve a protein structure, annotate it, and then give you some metrics. You can highlight it. And the idea is, this is, I had a talk at the TED Track last week, 2 days ago, and then the idea is this is distributable. So you can download the bulk data and run your own instance of TED if you like so. This is all based on Docker Compose, so you can run your own website if you want. So when is this going to be available? Soon. I hope like within a month. We're looking at the final refinements on the bulk data so that you can run your own TED. We're going to have to deal with the rest of TED, which is TED redundant. We just finished chopping all of it, and then we need to process it through our pipelines. And Ian is working at the moment on including these domain-domain interactions on the web pages. For the last month, we worked on validating homologs using HMMs. And this work is under review at the moment. We just got some extremely valuable feedback from the reviewers, so we're acting on that as well. And with this, I think that's it. Thank you so much.
Thank you. Questions?
Yeah, thanks very much for a really lovely talk. In your consensus method, you, I think, used your own and the other group's method. But of course, it will be also very interesting to learn how much agreement, disagreement is there to sequence-based methods like PFAM and so on.
Oh, yes. We didn't use PFAM specifically, but we used HMMs from Cath as well. So in the end, we only ended up with tools that actually act on structures directly, but we did benchmark on HMMs as well.
Were there huge differences? Because I think if you go by sequence, you will find, for example, disordered regions, etc., which in the structural data that you take from Cath and SCOP and so on is usually not present because it's not present in PDB.
So we did look into that, and in the end, we decided to kind of use just those, basically just those three. We didn't really notice that much of a difference, to be honest. HMMs were good as well, but in this case, we'd have had to add an extra layer of scans and everything on top of it. But in this case, we're just taking a structure directly and then pipe it through all three predictors at a time. In this case, we have to consider that we're also dealing with 370 million files at the time, so it's a bit complicated.
In some limited way, I would expect that folds that we have never seen before will be newer folds in terms of evolution. Otherwise, they would have more chance to be repeated and therefore have been discovered before. So you mentioned, you showed the distribution in organisms, but I couldn't see really if there is any correlation or what insight do you have in terms of evolutionary age for new folds?
Well, I mean, from a very quick look, it looks like a lot of them, they come from environmental samples. So I would expect to have a lot of this enrichment in novel folds in metagenomes, potentially. One thing that I like to look at some point is to see how many things are unique to databases like Magnify, for example, things that are not classified already in AlphaFold, and see if there is something else in ESM and see how ESM is actually enriched in this kind of data. But
my follow-up question is, how about ESM Atlas?
Well, ESM is a bit trickier to deal with. It's like 3 times the size, and the quality is also a bit lower, I would say.
I've got one more.
Okay.
Maybe a tricky one. In how far does the misrepresentation that is present in SCOP and Cath carry over now to your large resource. And let me give you an example. In SCOP, the biggest superfamily by far is the P loop. It had, I think,
in Cath as well.
Probably in Cath as well. And I think in SCOP it was Alexei Merlin, looking at the stuff and so on. And I think I always found that the P loop was classified because of a tiny functional motive in SCOP. I mean, Cath was automated, it's different. And I guess other less frequent families and so on, they were treated somehow differently, right? And in a sense, that is a kind of or that may be a misrepresentation, right? That I'm pretty sure exists in SCOP. I don't know about how it is about
it
Cath.
exists. I mean,
and now when you make SCOP Cath, when you make these structural databases the basis for your automated analysis, then these biases do carry over, right? And I got a bit surprised when you said the P loop massively expands. Well, then the reason is maybe because it is annotated originally differently.
Yes.
Because it was only by that functional motive, while others were maybe treated by their overall shape and whatever.
Okay.
Is that a problem or not?
It is. It is absolutely. So in no resource is perfect. In Cath, we call them cross hits, where basically we have domains that they are misclassified, and this can happen. To avoid this, in this case, whenever we benchmark tools, especially FoldSeek, for example, when we did that initial pilot work, we have what is called a golden data set, which is basically a set of domains where this been manually created, and domain boundaries, domain assignments, and the superfamily is identical between Cath and SCOP. So we are sure that these are extremely curated data sets in this case. This is how we try to avoid this. Not saying that this is perfect. We aimed for a 5% error rate on this, but I mean, it's there. It's going to be there.